Thank you very much. Yeah, so I want to tell you about some measurements that we did a couple of years ago where we, for the first time, measured the spectrum of radiation from a horizon, in this case from an analog black hole, rather than from a real black hole. Unfortunately, we weren't able to get a hold of a real black hole to put in our lab. I guess the SSC wasn't running yet. So let's remind ourselves, it was back in 1974 that Stephen Hawking predicted that black holes were not black objects. They didn't simply absorb things, but there was some sort of funny quantum instability, a quantum instability we really still don't understand, just near the horizon of the black hole, which caused the black hole to emit thermal radiation with a temperature proportional to 1 over the mass of the black hole. This was a real surprise to everyone, but Bekenstein had suggested already in 1972 that maybe black holes have an entropy. Largely this was based on work that both Christodoulou, who was a fellow graduate student with Jacob, and Stephen Hawking had done just before that, which suggested that the area of a black hole always increased. At least if all matter had positive energy, then the area of the black hole would always increase. And it's clear we've got this one thing, the area that always increases, and we've got this other thing called entropy that always increases. So therefore they must be the same thing. It's really a bad analogy, but it was really right. In trying to sort of justify it, he had to go through a number of contortions. Bob Garrosh already suggested, when he first heard about this, a little experiment of lowering boxes towards the black hole to show that if this was really an entropy, that one should be able to violate the second law of thermodynamics. And Bekenstein came up with a number of suggestions as to maybe there were some new laws of physics that you had to introduce that, for example, limited the entropy to energy ratio, which could save the second law of thermodynamics. But with Stephen Hawking's work in 1974, one could simply go ahead and recall TdS equals dE. E for a black hole is obviously just the mass from mc squared. The temperature we know is proportional to 1 over mass. And so we could integrate this equation to find an entropy. And lo and behold, the entropy was just 1/4 of the surface area of the black hole. Furthermore, one didn't need any new laws of physics. For example, this is Garrosh's argument. You have somebody with a big box. That box is filled with thermal radiation, which you lower down towards the black hole. If you lower that box right down to the surface of the black hole, then you can extract all of the energy of this radiation in there. You now open the box, drop this high entropy radiation, but it has no energy because you've extracted all the energy. Therefore, the surface area of the black hole wouldn't increase, but you've lost all of this entropy, violating the second law of thermodynamics. However, it turns out that if you have an accelerated system, and in general relativity holding the box near the horizon of the black hole is an accelerated system, that accelerated system sees itself surrounded by a bath of thermal radiation where that temperature is proportional to the acceleration. Now when you lower the box towards the black hole, you find that this external radiation provides a buoyant force to the box, meaning that the tension in the rope is less by that buoyant force. Therefore, you cannot extract all of the work. All you can do is to lower the box down to the point at which Archimedes would tell you that this radiation, the buoyant force would just be equal to the weight of this radiation in there. If you lower it any more, you have to do excess work on the system. And that turns out exactly to save the second law of thermodynamics. You then, at the floating point, open the box, let the radiation fall in. You haven't extracted all of its energy. That increases the energy of the black hole. As a result, it increases its entropy. And that's just enough to compensate for the entropy that you dropped in the thermal radiation. Now, this whole question of what the entropy of a black hole is has become extremely controversial. Although there seem to be only a few of us on the one side of this controversy by this time. But this isn't what I want to talk about today. There's a problem with Hawking's derivation, and that is that it really makes no physical sense. It's completely mathematically correct, but physically it is nonsense. Why? Well, let's look at this radiation that's emitted after the black hole has formed. Where does it come from? Well, as always in physics, what happens now happens because of what happened in the past. So we go down into the past to ask, where did that radiation come from? Well, we trace this radiation back. It comes from very near the horizon of the black hole, and the further back we go in time, the closer, exponentially closer to the horizon that becomes. The wavelength decreases by that exponential blue shifting, and eventually you get down to the point where the black hole was formed. Then this radiation comes from out here, and so we find that the radiation emitted out there really comes from the vacuum fluctuations in the past, but those vacuum fluctuations have a frequency of, let us say, e to the 10 to the 5th, if we look at a solar mass black hole 1 second after it's formed. Well, e to the 10 to the 5th is a very big number. It's so big I don't have to tell you units. No matter what units you use, whether it's Planck units or masses of the universe to measure your energy, all those units will do is make some insignificant difference in this 10 to the 5th. And it's absolutely clear that Hawking's assumption about this radiation is complete nonsense. If this fluctuation has an energy of e to the 10 to the 5th times the mass of the whole universe, then clearly it's not going to propagate just as this free scalar field in the vicinity of the black hole. One surely has to take into account the self-energy of these fluctuations, etc. So does this mean that Hawking, was all a nice idea, but the last 25 years or 30 years of theoretical interest are complete nonsense? Well, we hope not. Experiments would, of course, be determinant. If we could find a little black hole and we found that little black hole actually radiated, then no matter how uncertain we feel about the derivation, it's got to be right in some sense or another. But small black holes are very hard to find. Now last year, yes?
Just a comment. There's another derivation which just relies on having vacuum boundary conditions near the horizon, and you don't have to go over planking. I think.
Yeah, I've made that argument in the past. It's a hand-wavy argument, and if you really trace things back into the past, in other words, argue that what happens now is what happens in the past, this is the argument that you get. Last year I was very lucky. There were two conferences that I went to within about a month of each other. One of them was at Niagara Falls. This is the Canadian Falls up at Niagara Falls. And the other one was at Iguazu Falls in Brazil. Both falls have about the same volume of water going over them. The Niagara Falls are much, much, much thicker, much more water per meter of falls. The Iguazu Falls extend over about 2 kilometers, and this is just one small section of them. The reason I bring this up is that back in 1972, I was asked to give a colloquium in Oxford on black holes, and I was trying to think of what is a good way of explaining what black holes were all about. And the model I had, this is not the original slide, but the model I had was, let's imagine that we live in a world, we're a bunch of fish living in this world, which happens to have this waterfall. And these fish, as you notice, have no eyes. And these things are not fins, they're ears. These fish experience the world only through their sense of sound. Now, this particular world happens to have this very virulent waterfall in it, such that at a point over here, the velocity of the water going over the waterfall exceeds the velocity of sound. If we did this in our world, it turns out that the height of this waterfall would have to be about 100 kilometers. So it'd be a little difficult. So perhaps we could imagine this is set in Terry Pratchett's Discworld. And in Discworld, all of the human activities have to do with magic. And perhaps in this world, it's the fish that became physicists. And so these fish have, that's the professor sitting over there, and this is one of the graduate students who happens to have swum a little bit too close to this surface. Now, if that graduate student yells out here, then of course the sound waves will travel out away from where the fish yelled, travel out and eventually reach a supervisor. It's not clear the supervisor will do anything, but at least he'll know. But if this fish yells at this point where the velocity of the water equals the velocity of sound, then that sound wave that's traveling out will travel as fast as it can and never get anywhere, just like the Red Queen and Alice. And all the other sounds traveling in other directions will be swept over. Furthermore, if this fish were to be yelling, for example, help as it fell over the waterfall, what the professor would hear would be something like, help! The P would never get out because it was emitted just after it crossed that barrier. And the other stuff takes a longer and longer time to get out, i.e. it would be base shifted. And this is precisely what happens with light in the vicinity of a black hole. I.e., if you were to fall into a black hole, somebody looking at you would see the light coming from you very drastically and rapidly redshifted, and you would never be able to see any light that was emitted beforehand. So anyway, I gave this little example, and then about 10 years later, while I was preparing a course in fluid mechanics at UBC, my mind was wandering, and I suddenly realized that this analogy was actually a little bit better than I'd thought. Namely, if we, for example, assume that the velocity is irrotational, so that the velocity has a potential, then the small fluctuations in that velocity obey a wave equation, just like the scalar wave equation around a black hole. And there's furthermore an effective metric, just a given by the velocity of the water. If this was purely radial, for example, then you get something that looks like, for example, if I take C, that's supposed to be V. If V equals the square root of 2m over r, then in fact this metric is exactly the Schwarzschild metric in Painlevé-Goulstrand coordinates. So what we get is a scalar field behaving in exactly the same way as if it were traveling in a background Schwarzschild metric. Furthermore, one can go through Hawking's arguments step by step and obtain that this surface, where the velocity of the fluid equals the velocity of sound, should also have a temperature by exactly the same arguments that Hawking gave, where that temperature is proportional to the rate of change of the velocity as you go over that sonic horizon. The temperature is purely determined by the geometry of the background flow. if one is doing hydrodynamics, this suffers from exactly the same high-frequency problem. But of course, we know that hydrodynamics breaks down. One can't have sound waves whose wavelength is shorter than the interatomic spacing.
What about the units?
Pardon? Units, I think we're okay. No, there's some H bars and Ks missing in there. Pardon? Exactly the same way as Hawking got it into his. Step by step. So in fact, it's just H bar over K should be out here. Pardon? So you have the quantum fluctuations in the velocity field, in the velocity potential, in the region in which the space-time is flat, exactly like you have the quantum fluctuations in the scalar field in the black hole case. So one of the questions is, does this destroy the effect? Or do those ultra-high frequencies have any effect on the phenomenon? Well, I didn't know how to do the calculation, but fortunately I gave a lecture in Texas on this, and this infected Ted Jacobson's mind, and so about another 10 years later, Ted Jacobson realized that the crucial thing was that the atomic nature of matter alters the dispersion relationship of the sound waves. In other words, at high velocity, sound just doesn't travel at the same velocity as it does at high frequencies. It doesn't travel at the same velocity as at low frequencies. For example, you all have done the problem of little atoms on springs. If you did, Cattell or something like that, and you get a dispersion relationship which looks just like a sine wave, the opposite traveling guys give the dispersion relationship that looks like this. If you do neutron scattering on liquid helium, you find a dispersion relationship which looks like this. This is sometimes called the Roton minimum. And eventually it gets a complete mush once you start getting wavelengths that are of the order of the interatomic spacing of the liquid helium. So all materials have these altered dispersion relationships. This is, for example, the dispersion relationship for water waves in the transition between so-called deep water waves, i.e. waves which are shorter than, whose wavelength is shorter than the depth of the water, to waves whose wavelength is larger than the depth of the water. For long wavelengths, we have again this nice linear dispersion relationship, omega equals plus or minus k, and at high frequencies, that dispersion relationship turns over. Now, if the water is flowing, then the thing that's conserved is basically omega plus vk is equal to this dispersion relationship. Gives the relationship between the wave number and the frequency is conserved if the flow is stationary flow. So what one finds is that there are actually three solutions for k in this case. One gets the long wavelength solution for k. These are the so-called shallow water waves, or very long wavelengths. And one gets the deep water, the two deep water solutions for omega over there. Or if we go ahead and instead plot omega as a function of k, we have to take the v minus k over on the other side. We get a dispersion relationship that looks like this. The phase velocity is just omega divided by k, i.e. the slope of that line. The group velocity is the tangent there. Notice that the group velocity can go negative, or the group velocity over here can go negative, so and can do interesting things. Now, all of this stuff, back in 1981, I published it. And one of the things is I had a title with a question mark at the end. Now, Scott Tremaine has this theorem which says that any time you have a paper with a question mark at the end, the answer is always no. However, in this paper, that was a genuine question mark. I had no idea. Maybe one actually could do experiments in the lab in order to see these kinds of effects. And in fact, you could say that I've spent the last more or less 30 years of my life simply erasing one question mark. So I can now retitle that paper as Experimental Black Hole Evaporation with no question mark. That's of course not what we actually titled it. The title of the paper was Measurement of Stimulated Hawking Emission in an Analog System. It wasn't just me. It was a group of 5 people. Silke Weinfurtner was my postdoc. She's a theoretical postdoc, took her degree under Matt Visser. She was the one that really drove the experiment, the one that kept phoning us up at 11 at night to make sure we got back into the lab, or the others got back into the lab. Made sure that I bought all of the right equipment, and did all the jobs I was supposed to do in order to run this experiment. Ted Tedford is a postdoc here now, actually. He was a civil engineering student. He's in the Marine Research Institute. He was a recent graduate student of Greg Lawrence, who is a civil engineering professor. And he was the one that brought to us all of the experimental techniques that allowed us to do this experiment. Matt Penrice was an undergraduate student, both as a summer job and as a senior thesis project. So he was one of the ones that would have to go into the machine shop and carve out the various bits and pieces to make sure the experiment worked. Myself, I'm usually a theorist. I did get my hands wet. Greg Lawrence, as I said, is a professor of civil engineering, working in hydrology and so forth. And crucially, he also was the one that allowed us to get a hold of these long flumes in which we could do the experiment. Those flumes are usually used for undergraduate teaching, and we more or less took them over from the civil engineering department for half a year. I think the civil engineering department was worried that we were taking over the whole lab, because in order to keep out light, we built this humongous tent around the experiment that kept getting bigger and bigger and bigger. And they were worried that we were soon going to take over the whole experimental hall. So this is just a summary of what I've said. There are many kinds of waves that you could think of, electromagnetic waves and waveguides or fibers, fluids, Bose-Einstein condensates, etc. In all of these, one should be able to make these kind of analog black holes and try and do experiments in them. They all obey different equations from scalar fields at very short wavelengths. And so we could use those differences to test the dependence of the effect, for example, the thermal emission on the short wavelength physics, and ask whether Hawking really does depend on ultra-short physics or not. Now I want to make a little digression here on amplifier noise and on the relation between classical physics and quantum physics. Let's say that we have a system, and I want a linear system, so x is supposed to be some input and its conjugate momentum p, and y is supposed to be some output with its conjugate momentum p. Now we want an amplifier. We want a phase-insensitive amplifier, which basically means that both y and p are amplified by the same amount. And we write down this equation up here, y equals ax and py equals ap. Does that work? The answer clearly is no. Because if I take the commutation relationships between y and p of y, I get I times a squared. Well, I times a squared ain't I, unless a is equal to 1. So this would seem to say that the only possible amplifiers are amplifiers with unit amplification. But I go home at night and I listen to my hi-fi system, and it sure has different from unit amplification. So there must be something wrong there, and the answer is yes. Any amplifier basically needs at least 2 input channels. The second channel here is Q, with its conjugate momentum theta. Furthermore, that second channel is a phase inverting amplifier, namely that py is minus b times b theta, whereas y is just plus b times q. Now if I take the commutation relationships of y with p of y, I find this is I times a squared minus b squared. And if I choose a and b properly, that's equal to 1. I can make that equal to 1, and the commutation relationships are fine. Note that these coefficients a and b can be completely classically measured. I just send in a big signal, and I look at how big it is when it gets out. For any amplifier, of course, I can saturate it, where it becomes nonlinear, but as long as I'm working in the linear regime, I can completely measure these coefficients classically. But if I look at the system quantum mechanically, and I look, for example, at the reduced density matrix of the output, I find that the reduced density matrix of the output looks like e to the lambda times p squared plus y squared. This is just a thermal density matrix, where this coefficient lambda is just the logarithm of b squared over a squared. If lambda is also proportional to omega, the frequency, then this is in fact exactly a thermal spectrum. And I can determine that simply by measuring these classical things A and B. I can do this in terms of annihilation and creation operators, alphas and betas. I get exactly the same kind of thing. In this case, the alphas and betas are called Bogoliubov coefficients, etc. But this is all just classical amplifier theory, linear amplifier theory extended into quantum mechanics. The important thing here is that for these linear systems, one always has this norm, which I can define as I times, if Q is a solution, Q and P is a solution of the equations of motion, then I times Q star P minus P star Q is a conserved inner product. It's obviously not positive definite. In fact, if I go ahead and if this has got a positive norm, then Q star itself will have a negative norm. One can do this for quantum fields as well, and then it's just phi star pi minus pi star phi. And in quantizing a linear system, for example, a linear scalar field, it's these positive norm, not positive frequency. It's these positive norm solutions that come in as multiplying your A's, and the negative norm ones as multiplying your A daggers. So one can have negative frequency but positive norm states, and in fact these will typically occur in what we'll look at further down the line. But it's these norms of these classical solutions that is going to determine what the amplification and so forth of the system is. So the lesson to take from this little digression is that the quantum noise is completely determined classically. If you believe in the commutation relations of quantum mechanics, nothing fancy, just that you have commutators, then once you understand the classical mechanics of a linear system, you immediately know how much quantum noise there is as well. So let's get to the experiment. The experiment we did not with sound waves, but with surface waves in a fluid. We have water flowing down here. It flows over an obstacle. It obviously has to flow faster over the obstacle in order to conserve the amount of water. Over here, if it flows fast enough, over here we'll have a black hole horizon. Here we'll have a white hole horizon. And it turns out to be far easier to do the experiment with the white hole horizon than the black hole horizon. But the white hole horizon is simply the time inverse of the black hole horizon. Black holes are things that things can fall into but can't come out of. White holes are things that things can come out of but can't fall into. Just do the time inverse of a black hole, you have a white hole. So all of the quantum mechanics, which is time reversal invariant, is the same for white holes as for black holes. But in this case, what we have is we can send in very long wavelength waves. They will pile up on this horizon, eventually their group velocity drops low enough that they get swept out as short wavelength waves. And one can measure those short wavelengths far more easily than one can measure the long wavelengths. Our long wavelengths, for example, were up to 60 meters. Our tank is only 5 meters long. It's really hard to measure a 60-meter wavelength in 5 meters. Yes?
So classically, things come out of white hole, but nothing falls in.
Right.
I would have thought that if you do the experiment with the white hole, you need to somehow measure a small amount of stuff going into the white hole.
Right. Right, so here is a wave that's heading in towards the white hole, a long wavelength wave that heads in towards the white hole. It piles up on the horizon, just as going backwards in time with the black hole, that's just a white hole, the radiation, the long wavelength, kilohertz radiation from a black hole piles up near the horizon and produces that very short wavelength radiation initially. Well, that's exactly what's happening, only now forwards in time here. Long wavelength comes out, short wavelengths go back. So this is the paper. Again, the various people involved. Here's a drawing, and I like this drawing because the drawing looks exactly like the kind of thing you could get from a 19th century textbook in fluid mechanics. Much of our experiment is precisely 19th century type of stuff. We'll discover there's a few 20th century, 21st century wiggles that we put on top of that. We have a long flume, a pump here to pump water from a holding tank. It goes through here, a bunch of meshes here to get rid of the turbulence of the incoming flow. We have this flow traveling out here. This is just a frame to hold the plexiglass that forms the sides of the tank. Goes over this obstacle, speeds up over the obstacle and produces a white hole and black hole horizon there, and eventually falls over this weir into the tank again. By raising and lowering this weir, we can control the height of the water that's flowing down through the tank. This is our wave generator here with a motor which dips this screen in and impedes the flow and produces waves which travel back upstream. It also, of course, produces waves that travel downstream, but they just fall off the edge of the universe. This is the dispersion relationship that we get. In the upstream part of the flow, here's the dispersion relationship. For a frequency omega here, we get a solution, an incoming solution that's over here, i.e. its group velocity and its phase velocity is negative. Its group velocity is such that this gets dragged over here through the white hole horizon over here. On this side, we find three solutions. These two guys have the same group velocity as that one, namely being dragged down this way. This one is the incoming wave, very long wavelength, they've all got the same frequency. Frequency is conserved, but this is a long wavelength wave that travels upstream towards the white hole horizon. These two have positive norm. This has negative norm. Similarly, this has negative norm. i.e. norm and frequency are not the same thing, and it's norm that's important for the quantum mechanics. Notice that as we increase the frequency, this wavelength, this wave number gets smaller, i.e. the wavelength gets bigger, and this wavelength gets bigger as the frequency increases. We'll see that in the diagrams later on. Now, in order to do this, we had to measure the surface of the water. How do you measure the surface of water? You could get a bunch of plastic ducks and float them in there and measure the plastic ducks. But of course, you can't measure them very accurately. You could put little probes in, but that's going to upset the flow. Well, this is where Ted Tedford brought his brilliance in. What you do is you fill the water with rhodamine dye, and rhodamine dye fluoresces when it's hit by the green laser light from a green laser pointer kind of thing. So we had Well, we only used 0.5 watt, an intense green laser diode, which we spread out with a power lens. So it's a very, very thin sheet, which now shines on the surface of the water, causing the rhodamine to fluoresce. That's extremely helpful because one of the things you know about laser light is speckle. Whenever you look at a laser light, it's always got all these little spots in it that are constantly moving. Well, the rhodamine dye destroys the coherence of the laser light. The pink light that's given off by the rhodamine when it fluoresces is completely incoherent, doesn't have any twinkling in it at all. So one can very accurately, and the optical depth of this green light in this dye is less than 1 millimeter. So one can determine where the surface is very accurately. In fact, by doing interpolation, what we do now is we take a camera and take a picture of the surface. And by doing interpolation, we can in fact determine where the surface is to about 1/10 of a millimeter. So these red dots, these are 1 pixel on the camera. So 1 pixel on the camera is just a bit bigger than 1 millimeter. But by doing interpolation, these black dots, one can figure out where the surface is down to about 1/10 of a millimeter. In fact, when you do Fourier transforms, and this is an example of a Fourier transform of the tank with no obstacle in it, one finds that the error in these amplitudes for these waves is almost down around 1/100th of a millimeter. So one can very accurately measure the surface of the fluid just with a high-resolution camera and a green laser pointer. This, by the way, these are the spots that we measured. This is a Fourier transform both in space and in time. And the black and the red curve are the calculated dispersion relationship for waves on the surface of this water, with only one fitting parameter, namely the velocity of the fluid. Notice that we're doing pretty well. One of the things that bothered us was that there seemed to be this extra branch in here that for a long time we couldn't figure out what it was until Ted suddenly realized, wait, these are the transverse modes. So these modes are the modes in which the waves are uniform across. These are the modes where you get that's actually the second standing wave pattern across the tank. The first one has a node where the laser, that would occur about here, has a node where the laser is shining on the water, so you wouldn't see it there. So one really has a pretty good accuracy. Okay. Here we go. Here's a movie. This is one of the old wave generators that we had. Here's the water. This has a slightly different dye because at that point we were using slide projectors in order to form the little sheet on the top. Notice this wave, long wavelength wave, is traveling up. It gets to the obstacle, and it can't get beyond the white hole horizon sitting here. And it converts to waves being dragged away, whose group velocity is less than the velocity of the fluid, which are these little ripples that you see in the top of the fluid. We can see that, we can see that a little bit better. What this is a picture, 18 seconds worth of time over 2 meters. We send in a wave packet. These false colors are the heights of the waves. And we notice here that the wave crests travel towards the horizon, which sits here, but the wave packet comes in towards the horizon, then turns around and gets carried away again. Notice that the group velocity is away from the horizon. The phase velocity is still towards the horizon. One of the things that always confused me when I was an undergraduate was this difference between group and phase velocity. And here's a really nice example of the difference. The phase velocity is going in exactly the opposite direction to the group velocity of these waves. This is one single frequency, continuous frequency, and the main reason I'm showing it is that in the adjacent channels, we're getting no leakage. So these are the adjacent temporal channels. What we did was we made sure that we kept a number of, the time that we actually measured things was an exact multiple of the period of the waves that we were sending in. That meant that you didn't get that Lorentzian kind of shape for the peak, the Fourier transform peak. One got a delta function at a single pixel location. And this gives us a feeling for the noise in the system. This channel is the signal that we sent in, and these are the waves that are coming out. And these channels are the adjacent channels, which are the noise, and you're basically seeing no noise whatsoever in those adjacent channels. If we took the Fourier transform and then simply took the outgoing waves and threw everything else away in the Fourier transform, did the Fourier transform back again, we got this. These are the positive norm waves that are given off by that horizon. That are being dragged away from the horizon. Notice that their phase velocity is still towards the horizon, but the group velocity is away from the horizon. And these are the negative norm waves that are carried away from the horizon. And this is just a plot showing you what the full spectrum looks like at specific frequencies. So there's two possibilities here. 0.02 hertz, that's basically 50 seconds. The period of these waves that we're creating is about 50 seconds long. Notice that the incoming waves, this is the incoming wave. These are the outgoing waves, and notice that the two outgoing waves have exactly the same amplitude. That's exactly what you would expect if the temperature were equal to 0, because the temperature, remember, is proportional to the logarithm of A over B. So if we now look at the logarithm of B over A, if we now plot the logarithm of this reflection ratio of these outgoing positive and negative norm waves with respect to each other, then if we go through Hawking's calculation, it says that this should be a thermal spectrum. In other words, it should be linearly proportional to the frequency. The logarithm of this should be linearly proportional to the frequency. Well, here I've plotted the logarithm of that ratio for the waves that we have as a function of the frequency. The statistical errors, at least, are roughly the scatter of these points around that line. And I think you'll agree with me that that's a pretty good straight line. Yes? Yes. By this time, remember that the logarithm is down at 10 to the minus 5, so the height of the negative norm and the height of the positive norm the height of the negative norm is starting to get down into the noise. What you're going to do is, if you try and go any further, is you're simply going to get noise over here. In other words, this is all that we can measure in our experiment. Would there be some deviation eventually? Probably yes. But we don't see that in the experiment. What we do see in the experiment is this beautiful straight line. And remember that the real experiment, unlike the theory, has things like turbulence. In other words, the water as it flows over this obstacle is not irrotational. We did measurements of the velocity, the vertical profile of the velocity of the water, and you find that it goes more slowly at the bottom than at the top, as you'd expect. It seems to be laminar flow, but certainly not irrotational flow. Various other difficulties that one gets in the real world as opposed to the simple models one looks at, none of them seem to have any effect on the thermality of the spectrum. Furthermore, one can try and compare what one sees there to the derivative of the velocity of the fluid near the surface of the horizon. This turns out to be much more difficult because figuring out exactly where the white hole horizon here is actually quite difficult. And it's something that we're still working on. But somewhere between about here and here is what the surface gravity of this black hole is. The value that we measure from that ratio and that previous transparency is this red line, i.e. the temperature that you would expect from the water flow and the temperature that you measure from the positive and negative particle creation is the same to within a factor of about 1.5. N is the normal, surface normal along the direction of flow. So the conclusion is that this white hole horizon of the fluid in the flume would emit quantum radiation, properly spelled if it was doing it, with a thermal spectrum. If one calculate the frequency of this spectrum is about 1/8 of a hertz. It's about 1/8 of a hertz, which corresponds to a temperature of about 10 to the minus 12 Kelvin. So one of the questions is, did we in our experiment actually see the Hawking radiation, the real quantum particles given off by this horizon? The answer is unfortunately no. In Vancouver, our water is a little bit warmer than 10 to the minus 12 Kelvin. Besides, the amplitude of those fluctuations would also have been a little bit less than a 100th of a millimeter. So from both points of view, it would be difficult to see it. However, because we know that the quantum mechanics is completely determined by the classical mechanics of the system, and the commutation relations of quantum mechanics, we can argue that this is the first observation of Hawking radiation in this system. Thank you. Barry. Sorry, the frequencies, so the wavelength of the emitted radiation was about 20 centimeters. So the incoming radiation had wavelengths from 60 meters down to about 5 meters. The outgoing radiation had wavelengths of the order of 15 to 20 centimeters, that kind of range. Yes. Oh.
Sorry, it's a simple question. You kept saying that the frequency was the same and the wavelength was changing.
Right.
But at the beginning you said the problem could be mapped to an exact analog of the black hole problem.
Right. So in the black hole you get the same kind of thing. The radiation, as it gets towards the horizon, stays the same frequency until you get to the regime where the black hole is actually forming. Then you get this time-dependent metric, and that releases the radiation out as this very high-frequency radiation. Now, in the case of a black hole, if you didn't have that, it would just stick against the horizon forever, exponentially blue shifting forever, and becoming very difficult to figure out what in the world you're talking about when you talk about the initial state. It's just that when you look at in the water case, on the other hand, what releases those modes that pile up near the horizon is the dispersion relationship. Once one gets a short enough wavelength, then the group velocity drops low enough that the velocity of the water now sweeps the waves away from the horizon, and they no longer pile up anymore. But that also means that since the fluid flow is stationary, omega has to be conserved for any kind of linear wave traveling in this background. So the frequency in this case is conserved. It's the wave number that gets squeezed from a large value down to a small value. Now in this case, it doesn't get squeezed down to 10 to the minus 5, e to the minus 10 to the fifth. It just gets squeezed down from 10 meters to a few centimeters, because the dispersion relationship changes rapidly enough in the case of these surface waves of water. An interesting thing that one might like to do is to do this experiment not this experiment, but do this experiment with sound waves in liquid helium, because in liquid helium, that same dispersion relationship would drive the sound waves into the regime where you got that complete mess in the dispersion relationship. In other words, where the atomic nature of matter became really important. And if one then saw thermal emission being given off by one of those liquid helium horizons, it would tell you that it's, the emission is completely independent not only of, the high frequency physics, but even where the high frequency physics just seems to fall apart and just give you a complete and utter mess that you don't know how to calculate. Where you're really worried about individual atoms bumping into each other instead of these collective motions of the sound waves. Unfortunately, with liquid helium, you could imagine forcing liquid helium through a Laval nozzle so that it went supersonic on the other side of the nozzle. Unfortunately, the pressure you need to do that is enough to solidify the liquid helium while you were pushing on it to try and get it through the nozzle. And solid helium, unfortunately, doesn't work nearly as well. It's only by about a factor of 2 or 3. So maybe somebody could be very smart and be able to do it with liquid helium as well. But that's a far more difficult experiment. I'm a theorist doing an experiment. I've got to do easy experiments. Plus, NSERC would not give me the money for that.
I want to ask about these Laval nozzle experiments.
Right.
Is there a history of doing this with water or air and trying the equivalent?
No. Nobody is with water. You really have to get the water going at 1.5 kilometers per second, which is a huge velocity, and it's a huge pressure you would have to place on it. For gases, in a rocket motor, you typically get that happening in a rocket motor. The problem is that there you get such high temperatures and so much turbulence coming out that there's no way that you could ever see any of these effects in that case.
This is very amusing and beautiful.
Thank you.
What is it that you're testing?
What is it we're testing? What we're testing is the robustness of the Hawking prediction for the thermal emission from a horizon. What we're showing, one has done some of this numerically as well in other kinds of systems. What we're showing is that the thermal emission is extremely robust to whatever is going on at high frequencies. So that, the worry in the black hole case that perhaps the fact that, you're going to these absurdly high energies and so forth, really to some extent gets laid to rest, that it doesn't matter what's going on at high energies, at short wavelengths, etc. You're always going to get this thermal emission. Or as I like to phrase it, the thermal emission is really a low energy, long wavelength process. It's got nothing to do with short wavelength, ultra high physics, ultra high frequency physics. I can also then use that to talk about black hole entropy and so forth, but that's another talk. Yes?
This is presumably also relevant to reflection.
Right. So Robert Brandenburger, for example, and students and so forth have tried to use some of this in cosmology. One of the problems that I have with at least some of that work is that the dispersion relationship that they assume at very short wavelengths is bizarre, because the frequencies, they go up to Planck scale frequencies and then suddenly crash back down to 0 again. Now the problem is that if those frequencies are very, very low, i.e. of the same order as the scale at which things are happening around the black hole or in the cosmology, you would expect to get particle creation again there as well, right? So in that case, you'd expect to get excess particle creation, not just from the Hawking process, but also from the fact that these high frequency things are seeing a metric which is varying on time scales of their own frequency. And that's always going to produce particles for you as well. So it becomes very ambiguous, and I just don't believe that the dispersion relationship of anything is something that goes up the Planck scale and then crashes back down to zero. Maybe it does, but I mean, I think it's pretty unlikely.
Well, so it seems like this vindicates the viewpoint that you have essentially vacuum conditions at your
Yes.
That's what you need, and then as a result, you have essentially Hawking.
Yes.
It doesn't matter what you cut off.
Yes. Yes. Yeah, no, it certainly does. I mean, what would be nice is to really have a derivation which made that completely obvious. And that's hard to do. I've had trouble doing that.
You have a question? No. Other questions? Can you walk me through the white hole version of the experiment in terms of entropy? Where you were making decisions over here and sending information in and it comes back and some other.
Right. So one of the things about this system is that the link between entropy and horizons is completely broken in these cases. You can see it because the temperature where's that temperature for these guys? Somewhere in here. That temperature, we notice, depends on the flow, but obviously how the water is flowing doesn't give a damn about how much energy went into the system. So one has broken the link between the energy and the temperature. As a result, you can't use TdS equals dE, and you've broken the link between the material and any kind of notions of entropy. So they're really, talking about entropy. This is not a good analogy for entropy. It's a good analogy for temperature, but after all, the temperature was the important thing. It was because black holes had temperature that you then, assumed or calculated that they had an entropy. If one breaks that temperature, then the whole discussion just completely disappears.
If there's no further questions, just send the speaker again.
So there was experiment.
Well,